factor it out like that, and that would multiply into both of them. So I think that's where I was like, how do I factor this out? I knew what I was supposed to.
Yeah. Makes sense.
So that's just that's the note that I would have is.
Yep. So right. The place where most people have their issue is that factoring out part.
Yeah. Awesome.
All right, so now you have, this is doing implicit differentiation.
Mm-hmm.
What is that? What are we doing? Why are we doing that? What does that even mean?
It's a great question.
Thanks. All right, let's look at just simply, let's look at the 2y squared thing that we took the derivative of. So
sure.
As opposed to say, so we took the derivative of x cubed and the 2y squared. So when I take the derivative, what am I doing?
You're trying to find like a small slope almost. The derivative is like the slope of the function. You're trying to find something that's like very small.
That's right. That's right. And that that very small slope is dy over dx.
Yep.
And what we're trying to say is, literally slope means how is y changing according to x.
Mm-hmm.
Right.
Yep.
So in this, when I'm doing implicit, these variables are really important. So it's not like how does y change according to t or according to r or according to whatever. It's how does y change according to x. So when I take the derivative of x cubed, we can use our power rule, 3x squared. And then we know that the chain rule says if the inside part, this part, has a derivative, I have to take that into account.
Yeah.
Right? So if I did that, that would be the derivative of x with respect to x would be dx over dx, which is 1. It's the same. So when I'm taking...
that's why you don't write anything there.
Right.
You don't need to do anything.
I don't need to do anything because it doesn't have it's not changing with respect to itself.
Yep.
Its self is itself. However, in 2y squared, I'm still doing the same thing. I'm doing 4y to the first. But does y have a derivative with respect to x?
No.
Yeah.
Oh, sure. Yeah.
Sure does. What's the derivative with y of y with respect to x? Oh, it's dy dx.
It's dy dx, yeah. I see.
So anytime we have a variable that's not x, or the thing that I'm taking, like we could do the same thing, like let's say it was t cubed, and I'm taking the derivative with respect to t. Well, that's going to be 3t squared. Sure. But if I take the derivative with respect to t of s cubed, well, that's 3s squared ds dt.
Yeah. So that's how it differentiates with the y, between the y and the x. I see that. Because with the x, it's just dx over dx. It's the same. It's what it is. Same thing with the t. But when you're taking it in terms of like
on any other variable.
Yeah, exactly.
I have to take into account that variable could change. S could change with respect to t.
Totally. So it's not just its own thing, like how t is or how x is.
Right. Exactly. And then where this is really important is this is why calculus is very practical, because I'm taking into account in practical problems, like engineering problems, we do this all the time. How is the heat changing according to time? How is the volume changing according to time? How is the volume changing according to the heat? What?
Yeah. Yeah, you're not just looking at one variable. You're looking at how one thing may affect another. How yeah,
Exactly.
just like just how x and y affect each other with the slope. Yeah.
Yes. Yes.
Awesome.
Cool.
Yeah, that's funny. I don't know if I just was zoning out during the rundown of like what implicit derivatives are, if our teacher just didn't really tell us, because I don't really remember that. So.
I don't know your teacher, but in my experience, either most teachers gloss over it because they don't want to confuse
Yeah.
people, or they don't actually know. Not to be mean, but I think some
Yeah.
teachers don't
I
know
think
like why we're doing this exactly. But
yeah.
it,
Yeah.
anyway,